Yeah, no, you were.
I sat by myself and I made a lot of noise.
Oh yeah. You had as much as he won't I.
You're like, you made a lot of noise. Is that like
No.
you do your beats?
Yeah,
Alright,
something like that.
what's polar covalent mean?
That's positive and negative signs.
Okay, both nonmetals. There's a difference in electronegativity, a big difference, and right, asymmetrical. Right, asymmetrical. It creates those partial positives, partial negative. On the O is negative and the H is positive. Why is this called, and he's correct, hydrogen bond? Right. Hydrogen with O and a F, right? I say NOF. Enough. Or what did someone say? Uffin? Someone said uffin once. For some reason to help them remember. So molecules with these elements have special dipole. Where's dipole? This is dipole. This is hydrogen bond. It's the same exact thing. That force and this force are identical. This is stronger. It's called hydrogen bond because of these three high electronegative elements. So HF, NH3, and H2O, those are the three the Regents always uses. HF, H2O, NH3, which is over here. Those are the ones you're going to see. So anyways, what is the force of attraction? It's between two, right? So it's between the red and yellow. That's your force of attraction. That's your polar bond. That's the bond. This is the force of attraction. So it's a polar bond holding them together, but in between them, intermolecular is your hydrogen bond. Questions on this one? I'm more worried about this one than that one, for like Regents questions. Okay. Dispersion. What type of bonding?
There is.
Very good. Technically, it's called atomic bonding, but it's really just a bunch of forces. So he drew the dotted line. One xenon molecule or atom is attracted to another one. Very good, with a dotted line. But why are they attracted? It's okay. Anyone remember? The electrons all move. So all the electrons move to one side. If all the electrons move to the left side, and we split this in half like I did yesterday, what's the charge on this side? Negative. What's the charge on this, on the right side? Partial positive. Okay? So the positive here and the negative here, there's your dispersion. So even though it's just two atoms, right? These are very small. But if you had two xenon atoms,
Yep. Hey.
two atoms of xenon, at any given point, the electrons are going to all move to the left. So now this side will be partially positive, and this side will be partially negative, and they form a temporary dipole, which is really weak. So that's temporary, and it's like shaking hands and letting go, right? That's the analogy. So it forms, breaks, forms, break. That's really, really weak. This is really, really strong because that's a permanent. Those partial charges are permanent. That force breaks fairly easily, but it's a lot stronger than this one because these are not permanent. Once the electrons decide to come back over here, now this side's negative and that side's positive, and it doesn't make sense, right? It won't work. So that's why that's weak. So if we just throw in the positive, partial positive, negative, then we're good. So dipole moment here. This is very good. HCl is polar covalent, and the reason for that, the electronegativity of Cl is 3.2, H is 2.2, partial negative, partial positive. So if you take two of these and bring them near each other, one Cl is attracted to the other one's hydrogen. There's your dipole force, that dotted line. Everything here is perfect. That's good. All right, good job. Another way to see that, if I just show you an example here. Like this, right? So the red and the yellow, that's the dotted line between them, and that's because both Cl's are pulling all the electrons towards it, so you have your permanent dipoles. There's a dipole, that's why it's polar covalent bond, but that force is called the dipole interaction, or dipole-dipole. Okay, and this NH3 is just like this. It's the hydrogen of one and the nitrogen of the other. This was oxygen. this one here. This is nitrogen over here. So nitrogen or ammonia is polar. I'll show you that in a second here. But here's another way to see it. So I'm just going to draw it out. The way he did it was fine. But the N from this one, or this one, doesn't matter, is attracted to the H of the other, because N is partially negative, H is partially positive. Yeah.
So how come like the NH doesn't have like a dash in between like the H and the CL?
There's no CL here. What are you
No, 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 no. The question before that, right there, there's a dash between the H and the C. The dash,
CL.
the CL and the H next to the left.
So there's this,
Yeah.
and then there's this.
Right.
Which one are you talking about?
Yep, that dash right there.
Yeah.
How come there isn't a dash in
You
between?
just
the
asked
N-
him why there isn't a dash in between the N and the H of NH3.
Thank you.
Oh, I just didn't.
There is. There is, right here.
He's talking about the one at the top. Yeah, he's talking about the one.
Okay. I got you. Because this is just the chemical formula, not the dot structure.
He's
When
just
you
showing
write
you
when you
the-
write formulas, you don't show the bonds. The dashes are bonds. So HCl, that's the formula for hydrochloric acid. If I said draw the dot structure of hydrochloric acid,
Right.
it would look kind of like that. It would look like this: H with the dots around Cl.
Okay.
So we only show dashes when we draw like the dot structure. Who was this again? Silas? No.
Me.
Well, we'll just kind of abbreviated that. That's fine. Same thing over there. So she drew the dashes between the H and the L because that's kind of like the dot structure, but the official dot structure of water
Right.
looks like that. She just didn't show those dots. That's fine.
Okay.
Does that make sense?
Yeah.
Yeah. So he just didn't show.
Okay.
Okay, so N attracted to the H, there's your hydrogen bond. And again, if you look at the symmetry, this is polar because nitrogen pulls all the electrons because it has a 3 electronegativity and each hydrogen's 2.2. So each bond, remember each bond is treated separately. It's not like all 3 are ganging up on N. So N wins all 3. So N gets more of the electron density, so it's partially negative. And technically there'd be 2 dots here if you were doing the dot structure. So the N of one attracted to the H of another. That's your hydrogen bonding. Okay. Let's see, what didn't we go over? 1, 4,
7 to 9.
7, 9. Alright, so number 1. I'll just do these. Save a little bit of time. And then I want to show you something in the back. It's very simple, but we'll make it complicated. Alright, so CH4. Here's how I would do this. CH4 is attracted to another CH4, and I would draw it just like that. Here's why. So CH4 is a molecule, but I'm going to treat it as if it was just one atom. Here's why. These are so old. These were here when I got here, and who knows how long they were here before that. So the holes in the wood aren't really, doesn't fit very nice anymore. But anyways, the reason I do this is just for simplicity reasons here. How many electrons does CH4 have? 10. Yeah. 6 plus 4. If we split these in half. Now first of all, is this polar or non-polar, Shane? Polar or non-polar?
Non-polar.
Non-polar. Very symmetrical. If you were to do the dot structure of CH4, there it is. Very symmetrical, sharing equally, non-polar. So, all nonpolars in the world, every single nonpolar substance in the world uses what forces? Dispersion. So the answer to this is nonpolar bonds, dispersion forces. But how do we draw that? How do we show it? What is dispersion? It's when the electrons start moving. So I just make it a circle here because I say, all right, this side is going to be partially positive, this side is going to be partially negative. Let's say all 10 of those electrons start kind of migrating to this side. The same thing here. They start migrating to this side. So now we have those partial charges. There's your dispersion force. So that's what I would do if it was me doing the homework. I would show this side is partially negative, this side's partially positive, and it's temporary. You can't show that on paper, but it's temporary. Again, like shaking hands and letting go. So that forms, breaks, and that's how you show dispersion. So, especially Becky and Donatica, these partial charges, if you notice, we're writing them every single time. The only difference is there's different names. This is called dispersion, HCl was dipole, NH3 was hydrogen bonds, but they're all very similar as far as how they are attracted. Alright, so that's number 1. What's next? 4. 4 is literally the same thing. You have H2 attracted to another H2. Same exact thing here. Let's say the electrons all line up. There's only 2 of them. Each H has 1. So this is negative, this is positive. This is negative, this is positive. So again, nonpolar bond, nonpolar molecule, dispersion forces. How does it attract? That's how it attracts, the exact same way. So that's number 4. We did 5, we did 6, 7, and 9. 7 is the other type of, I put all 3 hydrogen bond molecules that are common on the regions on purpose. NH3, number 3, H2O5, and HF7. Those are probably the only 3 you're ever going to see on regions. And it's going to be even easier than this. This is a lot harder. Regents is going to say, which of the following contains hydrogen bonds? 4 choices, find the one with N, O, or F with H. And it's probably going to be one of those 3. So here's how we would do this. HF, attracted to an HF. And again, Tyler, I could show the bond here or not. It doesn't really matter. H is partially positive, F is partially negative. We've already learned why. Because there's a dipole, F has an electronegativity of 4, H is 2.2. This is a dipole interaction that's special because of fluorine, so it's called hydrogen bond. So there's your hydrogen bond. So it's a polar molecule with hydrogen bond. So that was number 7. And number 9 is just like number 2, which looks just like this. So this is not me being crazy. I did this on purpose as far as I wanted the homework to be repetitive. They all look literally the same except for this one. And that's the point. Partial negative, partial positive, you just have to remember which one's which. This is dipole because this is polar, and that's not an N or F, so it's dipole. That's hydrogen bond, these are dispersion because they're nonpolar. So yeah, it's confusing, I know it is. Alright, that's why I spend about 2 periods on it. Yesterday, today, going over the homework slow. This is just kind of a summary of what we learned yesterday and what I just talked about. Next Friday, I think I put up here, the 8th, you're going to have a quiz on bonding and forces. I'm not going to make you draw these things. Why do I do it then? Because who knows what the Regents is going to ask. This has been on the Regents. They want kids to draw hydrogen bonds. This has been on the Regents. This is pretty common. Alright, how to draw water attracted to an ion. But they make it easier. On the Regents, they do this. They would tell you, okay, potassium iodide dissolves in water. In the box provided, they give you a box, using the key, show how the ions in water interact. So they would say K plus is equal to this, and then they would say H2O is equal to that. They would say in the box, show how the K plus and the water are attracted, or how the K plus and the water interact. So they're basically leading you right to the answer. All you would have to do is draw the correct orientation, the oxygen facing the K plus. So what I did on homework here with you is even harder. I made you just come up with that on your own. All right. So I'm just trying to help you understand what you really need to know. I always teach a little bit above. So that's going to be Friday, and you will have a review sheet for that. Questions for me? Anything I just talked about? I know I didn't call on a lot of you or really interact too much, but I wanted to make sure I went over it slow. And I guess that's just what I want to do. I didn't really want to call on you too much. I had some examples, but no questions. Okay. You're going to need a whiteboard and a marker, and bring it back to the lab area. I'm going to have to pause this or stop it because